Atomic orbitals are a consequence of the wave properties of electrons in atoms. Many of the waves we talk about and see travel. The waves moving across the ocean are moving. But when we confine a wave in space, when we fix it at 2 points, in the example of this guitar, it's fixed here and here, then we change the wave behavior a little bit, and we can have what are called standing waves, waves that fluctuate in time but don't fluctuate in position, don't move. If we have these sort of fixed points at the end, the allowed energies of a guitar string wave, there's a low energy option where at one point it might be up in the middle and then another down in the middle. Okay, I'm going to label this as n equals 1. There's another allowed state that's higher energy, and in that state there's what we call a node. As it's fluctuating, two parts of the wave are sort of moving up and down, but there's this spot in the middle that's called a node, and this is a higher energy state, and we'll give it a number n equals 2. And this continues if we go to a third state. This one has 2 nodes. There, and this one would be n equals 3. And you can imagine there's an n equals 4 and an n equals 5, and each time they get to be a little higher energy. Another thing that happens is we change how tightly the wave is confined, we can change its energy. You change the pitch on a guitar by pressing down on the string between these 2 slightly raised metal bars called frets. And when you do that, it adds sort of a point of confinement there. The part of the string that's fluctuating now has a shorter wavelength. Recall that a short wavelength corresponded to a higher frequency, higher pitch. It's also a higher energy. And so as we change how the confinement happens, we can change the energy of these waves. Now we're still going to have an n equals 1, an n equals 2, n equals 3, but in this case, the n equals 2 is going to be higher. So this is a consequence of confining waves in space that we get these quantized or specific and discrete allowed energies that conform standing waves. Okay. Electrons in an atom, if they lack the energy to escape the atom, are confined in space too. And if let me draw it a different way. If we have a graph like so, and we look at the distance from the nucleus, the stabilization by that proton-electron attraction is greater the closer the electron is to the nucleus. And what this causes is sort of a well, a potential well, where the electron is effectively confined within a certain distance of the nucleus. Now, it's more complex than the guitar string problem because it's in 3 dimensions, and it's more complex because it isn't a fixed edge. But when we start looking at how electrons become confined in space, we end up with what Bohr was describing in his model of the atom as these energy levels. And we have something that corresponds to n equals 1, just like we did on the guitar string. And then a higher energy, so if we have energy on the axis, a higher energy would be n equals 2. And then a higher energy still would be n equals 3, etc. And it turns out the spacing between these gets narrower and narrower as you go up in energy, or these higher principal quantum numbers. So this is the principal quantum number. Okay. Because this is more complex, because of these 3 dimensions, when we solve the quantum mechanical equations, we get an interesting thing happen. When we have n equals 2, we have different ways that we can put that node into the atom. Some of it can be radial in the sense that you get the node as you move away from the nucleus, but there's another option that changes the shape of the orbital. When we talk about the n equals 2, we give these different shapes different names. So when we have n equals 1, we're only allowed the shape that corresponds to s. When we have n equals 2, we can have that same s orbital with a radial node, or we can change the shape and have a node in space, and we'll give that the 2p. When we get to n equals 3, we have a few more options. So in addition to the s, we can have the p shape that we saw with n equals 2, but we can also have a third option we're going to label d. And then 4s, 4p, 4d, 4f, etc. That number is the principal quantum number. The letter describes the shape or the angular momentum quantum number. Okay, so the letter's describing the shape. The principal quantum number is describing essentially how large, how far from the nucleus, because those higher energies allowed the electron to move farther and farther away. We can visualize the shapes of these orbitals. These are really mathematical descriptions of the probability density of a wave, but we can visualize them by making plots of a surface that contains typically 50% of the probability density, the likelihood of the electron being located in that area. And they end up looking like this. So this first red sphere is an s orbital. And remember, we can have a 1s, we can have a 2s, a 3s, a 4s, etc. Okay, we can have a p orbital. Now the p orbital didn't exist for n equals 1. So we started with 2p, 3p, etc. Now, there are three options for how we position this p orbital. It has sort of two nodes, or two lobes, with a planar node. There is no probability density in this YZ plane. Okay? Equal probability, it's on either side, but no density in that plane. But we can orient those lobes in three different directions. In this example, it's along the x-axis, and we label it the px orbital. If we orient that same lobe along the z-axis, we have another one that direction. That's the pz orbital, and along the y for the py. Okay. When we move to the d orbitals, there's 5, and their shapes get a little more complex. So again, these are consequences of those differential equations. But we would have 3d would be the lowest energy d orbital. We could have 4d, etc. And when we go to f, they're even more complex. Okay, and the lowest energy f orbital is 4f. Now that can be a little tough to remember, and so we often use a little just sort of diagram like this one on the right here that shows which orbitals are allowed. So 1s, but to get to p, we go to that second row, etc. Okay. When Bohr is looking at the hydrogen model of the atom, and he described the 1s orbital, and then I'll just put them in 2s, 3s, 4s. I'm going to leave a little extra space here, which will make sense in a minute. All the s and p and d orbitals, all the shapes would have essentially the same energy until we add a second electron. And when we add a second electron, we have an effect called shielding, okay, where an electron that's in between, if we have an electron in between an electron and a proton, it will reduce the attraction of that second electron a little bit because the two electrons have a repulsive interaction. And so what happens there is the different shapes of orbitals destabilize to different extents. And the p orbital is more effectively shielded, so it moves to a little higher energy. Okay, and so the 3p will be a little higher energy than the 3s. Okay, and the 4p will be a little higher energy than the 4s. Okay, the d orbital is further destabilized, and it turns out the 3d orbital moves above the 4s orbital. And this orbital fill order, the relative energies of these orbitals, become important as we start to look at electron filling diagrams or understanding where electrons are located and what shapes their waves take in these atoms. Remembering this fill order can be a little bit tricky, and one trick to do that is to come back to this little diagram we wrote here. And if you draw diagonal lines down to the left, starting at the top, the first orbital to fill is the 1s orbital. The second to fill is the 2s orbital. Then we fill the 2p and then the 3s orbital. Then we fill the 3p and the 4s orbital. And then we fill the 3d, 4p, 5s orbital. And we can continue down that way. And that works very well for determining fill order at these lower energies sort of down here. As you start getting larger, particularly as you get into the f orbitals, the energy spacing is close enough that the order of filling can be a little different. But these are the atomic orbitals and the shapes. Each of these bars that I've drawn in this orbital fill order diagram represents a specific orbital, one of those shapes, where we can put electrons. So think of them as little shelves to place electrons on.